All right, today we're pulling back the curtain on decision tree regression. Now, this is a really cool machine learning model because, unlike a lot of those complicated black boxes, this is one you can actually look inside and see exactly how it thinks. We're going to open it up and show you precisely how it takes a mess of data and turns it into really clear, understandable predictions. So, here's how we're going to do it. We'll start with a really simple problem, then look at how a tree actually splits up data to make its predictions. After that, we'll see how it stacks up against other methods, and we'll finish off by getting real about its strengths and its weaknesses. Okay, let's kick things off with a classic challenge. Imagine you're trying to predict a baseball player's salary. You don't have a crystal ball, but what you do have is data. Things like how many years they've been in the league, how many hits they got last season. The question is, how do you turn all that information into a single number, a specific dollar amount? And this is what that data might look like when you plot it out. See, every single dot on this chart is a player. They're plotted by their years of experience on one axis and the number of hits they got on the other. Now, their salary is kind of hidden in there, but right now, it just looks like a big cloud of points. So, where do you even start trying to find a pattern in that? Well, here is the beautifully simple idea at the very heart of a decision tree. Instead of trying to find some super complex single formula that fits that entire cloud of data, the model asks a much simpler question. What if we just chopped it up? What if we just sliced it into smaller, easier to manage boxes? Okay, so let's dig into how this whole chopping process, or what's really called partitioning, actually works to come up with a final prediction. And this, formally, is what a regression tree does. It's built specifically to predict continuous numbers. Things like a price, or a temperature, or a player's salary. It's not for putting things into categories like cat or dog. Now, the magic trick here is something called recursive partitioning. It sounds complicated, but it just means the algorithm does the same thing over and over. It makes one split, which creates two new groups. Then it looks at each of those groups as its own new, smaller problem, and splits them again and just keeps repeating that process. So, here we go. Here's the first move. The model scans all the possible features, years, hits, whatever, and finds the single best place to make one clean cut. In this case, it decides the best split is by years, right at the 4.5 mark. Just like that, all the players are in one of two groups, those with less than 4.5 years of experience and those with more. But it's not done yet. Now it zeroes in on just one of those new regions, in this case, the players with more experience, and it makes another cut. But this time, it uses a totally different feature, the number of hits. This helps create even more refined, more specific little groups within our data. Okay, so after all this splitting and slicing, how does the tree actually make a prediction? Well, this is the really crucial part, and it's surprisingly simple. For any new player, we just follow the rules of the tree down until they land in one of the final boxes. And the prediction? It's just the average salary of all the original players who ended up in that exact same box. That's it. No crazy formula, just a simple average. But wait a minute, that brings up a really big question, right? How does the algorithm know where to make these cuts? I mean, what makes splitting at 4.5 years better than splitting at, say, 7 years? The strategy it uses for this is called the greedy approach. And it's called greedy for a good reason. It doesn't think ahead. At every single step, it makes the decision that looks like the absolute best choice right now, at this exact moment. It doesn't worry about whether a different, less obvious split now could actually lead to an even better tree later on down the line. So how does it define the best split? Well, the main goal is to make the two new groups as internally similar as possible. In regression, that means we're trying to minimize the variance. You can think of it like this. The algorithm wants to draw a line so that all the salaries in one box are really close to each other, and all the salaries in the other box are also really close to each other. It's trying to create pure groups. Now, this whole method of making simple, boxy cuts is what gives decision trees a massive advantage, especially when you compare them to models that try to find one single perfect solution for all the data at once. So let's compare it to a classic model, linear regression. Now, linear regression always tries to fit one single straight line to the entire data set. It basically assumes that as one thing goes up, another thing goes up or down at a nice, steady, constant rate. But, real life is messy. It's hardly ever a perfect straight line. What happens if a house's price goes up with its size, but only up to a certain point, and then it kind of levels off. A single straight line just can't capture that kind of curve or that kind of nuance. And this is where a decision tree just absolutely shines. By carving out a whole series of these simple rectangular regions, it can actually approximate those complex nonlinear patterns that a single straight line would miss completely. It literally builds itself around the data's true shape. Of course, no model is a silver bullet. Decision trees have some incredible strengths, but they also have some pretty significant weaknesses. And understanding both sides of that coin is the key to knowing when this is the right tool for your problem. Probably the biggest strength, the thing people love most, is its interpretability. It's what we call a white box model. You can look right inside and follow every single decision it makes. It's also super flexible. It can handle all kinds of data without a ton of prep work, and it doesn't get totally thrown off by a few weird, extreme data points. Okay, now for the big weakness. The single greatest danger with a decision tree is its tendency to overfit. Because it's so flexible, if you don't give it a stop sign, the tree will just keep splitting and splitting until every single data point from your training set is in its own perfect little box. It doesn't just learn the pattern, it basically memorizes the data, noise and all. And that overfitting leads to some big problems, like high variance and instability. A tiny little change in your training data can cause you to get a completely different tree, and that means it's not going to perform very well on new data it's never seen before. Now, this is a huge issue, but it is solvable with techniques like pruning, which is like snipping off the least useful branches to stop the tree from getting way too complicated. All right, so let's put all these pieces together and talk about the final takeaway. What are the key things you really need to remember? The entire process really just boils down to these 4 steps. First, you start with all your data in one big pile. Second, you just recursively split that data, always finding the best feature and the best place to cut. Third, remember the whole goal is to make the resulting groups more pure or have lower variance. And finally, fourth, you stop splitting, and the prediction for any final box is just the average of everything inside it. And this really leaves us with a final, and I think pretty important question. In this world of ever more complex black box AI, where we often have no idea how a model arrived at its answer, there's a unique power in a model that can actually show its work. It makes you ask, is a simple, understandable answer sometimes more powerful than a slightly more accurate one that we can't explain at all?